Hello, everyone. My name is Lesley Carhart, and I first of all want to start out by saying how honored, humbled, and absolutely grateful I am to be here with you today, Women in Cybersecurity Middle East. I'm going to be talking to you today about a topic that's near and dear to my heart, industrial control system cybersecurity. I hope you find it as interesting and enriching as I do.
Well, first of all, who am I? Well, as I mentioned, my name is Lesley. I have spent about the last 20 years in IT, with the last 13 focusing in cybersecurity, specifically digital forensics and incident response. I'm a specialist in doing those tasks on industrial control systems. I'm also a speaker, a blogger, and a lecturer at several US universities. Now, today, I have a very short amount of time to try to convince you that you should join me in the space of industrial control system cybersecurity. So to do that, we'll have to cover what an industrial control system really is, where they exist and what impact they have on society, the cyber threats that they face today that we're battling constantly as cybersecurity professionals, and why it's increasingly critical day by day to secure them properly. And finally, as you've invited me to be a part of your community here, I'd like to invite you to be a part of our community of industrial control systems cybersecurity practitioners. We really need you to do a lot of the work that hasn't been done yet. It's a fascinating career that's incredibly valuable to be a part of. And I enjoy it very much, and I think that a lot of you will too. So we have to begin with understanding what an industrial control system really is. Now, industrial control systems aren't necessarily digital or computerized systems. They can be mechanical or analog systems as well as digital systems. There have been industrial control systems for thousands of years. Simply put, an industrial control system provides automatic control of a physical process. And those processes can be a lot of different things, almost infinite things. We'll talk about a few examples. So even things like simple gears and pulleys, something like a water clock, can be an industrial control system because it's automating some mechanical task. So a human being doesn't have to do each component part of the process. And systems today, they're not necessarily all cyber systems or digital systems. They can certainly be a combination of mechanical, analog, or digital control components. Some systems use all of those. Some systems only use one of those components. Obviously, from a cybersecurity perspective, we're usually less concerned about the analog or the mechanical control systems, but they can cause a big impact in our digital systems that we're looking at in terms of cybersecurity. Obviously, a system that has a combination of those control systems will be influenced by the digital systems in unpredictable ways, depending on the mechanical and analog systems in place. So I've been talking about processes. What's a process? Well, at a very broad, high level, a process is a series of discrete operations which accomplish some physical task. Now, what does that look like in reality? Well, it can look like all kinds of different automation things. So some ones that we see in our everyday life are things like water treatment and sewage. So turning on the faucet and water comes out. Pretty important to my life. I don't know about yours. I presume so. Also electrical power. Of course, in our modern society, we rely on electricity for infinite things. Oil and gas, obviously also a critical part of civilization today, is fueling our facilities, fueling power, fueling our vehicles, our aircraft, etc. Transportation and logistics. We live in an increasingly just-in-time economy, which means we have very, very fine-tuned logistic systems that get our packages, our deliveries, our storage of supplies to where they need to be in a proper amount of time. And we don't necessarily have massive warehouses of everything in our local cities. We have these complex systems that get boxes off shelves, use robots to move them across facilities, track them as they're shipped out, as they're received, using RFID, using barcodes, etc. So transportation and logistics use a huge amount of industrial control today because you don't want to have a human being handling every one of those tasks. It's inefficient. And then there's manufacturing. We've all seen manufacturing lines in videos or in person where there's robots doing all kinds of different tasks. There's conveyor belts running. There's all kinds of machines making parts and assembling them with minimal human interaction. So industrial control systems are all over the place in manufacturing today. Very, very important to our society, of course. And then there's building automation. So we don't think about this one a lot, but wherever you're sitting right now, if you're sitting in an office building or a university, there's probably heating and air conditioning systems. There are lighting and all kinds of power control systems in your environment that keep things from going catastrophically wrong if there's an outage. And most of those are industrial control systems as well. So obviously we are surrounded, absolutely surrounded by industrial control systems. They're all around us every single day. And they have a huge impact on our life. We don't normally notice that they failed until they fail. When you turn on the faucet and water doesn't come out, that's a rather alarming situation. Or when the power goes out, we notice that. We know how to deal with it, but it's still a nuisance, and we still certainly notice that an industrial control system has failed. So industrial control systems can be very, very simple things that just maybe control the air conditioner in your building, all the way to things that keep society functioning. So they're really, really important to our way of life. And again, these are oftentimes digital systems, not necessarily, but oftentimes computers. So what does an industrial control system actually look like? Well, industrial control systems are made up of something called control loops. And a simple control loop is made up of 3 parts. So it's made up of a sensor, which detects change or the condition of a system. So things like motion sensors, pressure sensors, temperature sensors, scales to sense weight, all kinds of different things that detect physical state of things or chemical or electrical state of things. Then there's an actuator. So your industrial control system is doing something in the real world. It could be a motor controller. It could be a valve. It could be a heat source turning on or off. So impacting something in the real world. So that's an important part of an industrial control system. But then you have to have something that does the decision making. So again, the controller can be all kinds of different things. It could be gears and valves that just keep running mechanically. It could be simple electronic circuits, or it could be computers, like many industrial systems today. And a simple computer that's programmed to receive a specific input from a sensor and do a specific thing to its actuator. So thinking about a simple process like a revolving door, you step into an automatic revolving door, and a sensor detects your motion and you being present in the door. And the controller's been programmed to start a motor. So there's an actuator for a motor there, and it makes the door start turning. Now, what happens if the controller fails and it doesn't start on time, or it starts too early? Well, you don't go through the door. Maybe the door stops and you hit it. It's not a very fun thing. We've all done it in a hotel or an airport, etc. But yeah, so we can think about some simple control loops in our life with these industrial systems, and what's failing when they do something wrong. Is it the controller being programmed wrong? Is it the sensor detecting something wrong? I encourage you to start thinking about the industrial processes that surround you every day and what these actuators and sensors are doing, especially the very simple ones in your daily life. And you'll start to understand industrial control systems a little bit better. Now, not to alarm you, but in real complex industrial environments, they're usually a combination of tons and tons of control loops. So all kinds of different control loops doing different things. So think about a manufacturing facility. Well, there's all kinds of things happening in time to one another. So they have to happen in synchronicity with one another. So you have maybe a conveyor belt carrying something along the conveyor belt. And then you have another industrial control loop that is dropping something onto that onto that conveyor belt. And you have yet another control loop that's packaging that box up. So those things all have to work together in the same timing. If they aren't in the same timing, bad things are going to happen to the articles on the conveyor belt. So you usually have some overarching control done by a human or done by a computer. And that's where we bring in things like distributed control systems, or SCADA. So if there's something I can get across to you today, ICS and SCADA are not the same thing. SCADA is something that does kind of overarching monitoring and control of a bunch of different control loops that usually have their own dumb controllers doing simple programming logic. SCADA is controlling a bunch of those together, just like a distributed control system is in a smaller environment. So I don't want to delve too much into terminology and devices today, but they're different things. And this is why. There are usually some kind of overarching control systems that coordinate a bunch of smaller, simpler control loops with their own simple controllers. And we kind of can break the industrial networks down into a simple academic model. Now, with all academic models in IT and in other things, they are not 100% reliable. They are not always accurate in every environment. They are there to help us understand what's going on. So don't take this as truth. It's just a simple example of what an industrial network often looks like to some degree. And we call this model in industrial networks the Purdue model for Purdue University, who originally developed it. And it's broken up into several levels. So these levels they start at the bottom from level 0 and they go up to level 4, sometimes level 5, depending on who's discussing the model. But at the top of the Purdue model, you have your normal IT corporate network, the stuff we're very familiar with. The network that you're sitting on with computers, checking email, going on the internet, etc. And then in an ideal world, you've got some kind of DMZ separating you from your industrial network with some kind of access control, VPN, jump hosts, etc., to keep it somewhat segmenting. We don't see much real air gapping in industrial environments, but we see a lot of this segmentation with a DMZ, of varying quality, of course. And underneath that DMZ, at the highest level, we have our more familiar IT devices. So our domain controllers, our workstations where our engineers do updates and programming to the systems, our database servers, et cetera, et cetera. So pretty familiar stuff. Beneath that, we have more of our control environments. So the next level, level 2, includes things like human-machine interfaces. So the computers that the operators look at to make changes. You've probably seen them in videos and in movies or in person. They're simple visual control interfaces that allow people to see the state of their system and perhaps make changes to it. Usually it's something like a Windows embedded computer. So something relatively simple, but still a more familiar type computer system at this level. Now, beneath that, things start getting a little strange. That's where we start having our controllers, our simple computers, ruggedized computers, things like PLCs. They're simple ladder logic devices, but they're still computers. They're running usually a customer proprietary firmware. So they're going to look a little bit different, but the programming is still not unfamiliar there. Those are simple computers programmed to do simple control of those control loops that we discussed. So not too hard to understand, but a little bit of a different understanding of firmware and programming there. Now, at the lowest level, we have the very, very simple electronic and mechanical and analog devices that feed inputs or receive inputs from those controllers. So those are things like our sensors and our actuators, simple motor controllers, temperature sensors, pressure sensors, et cetera, et cetera. Now, the thing to understand about the Purdue model is that each one of those levels of the Purdue model is a little bit different. So in each one of those levels, obviously at the very top, we talked about very familiar Windows type, Linux type computers. So things that we're very familiar with working with in IT cybersecurity. And as we went down the Purdue model, each level became a little less familiar. So we started getting into more ruggedized computers. And obviously, not only are the devices at each level different in function, but they're often different in vendor, and they talk to each other using different protocols. So the protocol communications between each one of those levels of devices is different than the others. So the simple devices at the very bottom might only send simple electronic or serial input to the controller. Now, the higher level devices, like the HMIs talking to higher level devices than them, might be using familiar Windows type protocols. It really depends on the manufacturer, the vertical, and the environment. But we have to understand that at each one of those levels of the Purdue model, we typically have a different set of devices that have different security concerns and a different set of network protocols, which could be TCP/IP and familiar, or something being transmitted over serial. So that's a really important aspect to understand about these systems. And all of these devices have different cybersecurity capabilities. The higher level devices that are typical Windows computers, even if they're older, they might support things like antivirus. So they have some security capabilities. And as we get lower level to the lower level devices, there are less and less security capabilities typically built in. So most industrial protocols, the vast majority are not encrypted. There's no security built in, and we'll talk about why that is. And we don't see as many security controls or ability to install security tools as we get to the lower levels as well. Now let's talk a little bit about the threats that these systems face. We've talked about what they look like. So I kind of break out the incidents I respond to into 3 categories. So the first one is insider threats. Obviously, a operator or engineer who's very, very familiar with their industrial system can cause a lot of damage. Realistically, the first thing I would term a cybersecurity incident in an industrial environment was an insider incident. It happened long before Stuxnet. It was in Australia. A disgruntled operator dumped a bunch of sewage out around 2000. He dumped a massive quantity of sewage out of a sewage treatment facility because he was angry about not being hired on full time. And it didn't make a lot of news at the time because we weren't thinking about these types of threats, but now I think about it. That was really the first case of what I would call a true cyber incident. And others will disagree with me, but in the way I categorize things as a cybersecurity incident targeting an industrial system. And they still happen all the time. People get angry and they can do a lot of damage with industrial systems. So it's something we have to be concerned with, and we do a lot of incident response in. And then there's commodity malware or ransomware, and we see a lot of that as well. Obviously, there's a lot of legacy devices in industrial networks. There's a lot of very simple computers that are things like XP embedded that are very vulnerable to commodity, even older commodity malware, things like Conficker and Sality. And those pieces of malware can have a big impact on low resource systems, even unintentionally. Even if they're headless and they no longer do anything overtly and purposefully malicious, they can simply fill up a hard drive or fill up memory. So commodity malware still has an impact. It spreads very easily in industrial environments if it gets in. And ransomware is a thorn in operators' side, not necessarily because it can infect those lower level computers. PLCs and other types of controllers will keep doing what they were programmed to do forever and ever and ever unless they're smashed or they fail. But what operators do lose when there's a ransomware infection in an industrial network is things like visibility of their systems. So they don't know what they're doing and they don't know if they're safe. So they often have to shut them down. And then, of course, we have our advanced adversaries. So those are people who are purposefully targeting industrial networks to do something kinetic to the world. It could be sabotage. It could be espionage, trying to figure out how a manufacturing process works. So it really depends on the adversary, but they're trying to do something specific and targeted. Now, what's the reality of these attacks? Okay, so first of all, the consequences of an industrial control system cyber attack can be very, very severe. We've talked about where those systems exist. Obviously, as well as processes failing, there's concerns of operator injury or loss of life, environmental contamination, major failures that permanently damage things like power or manufacturing facilities. So the consequences of industrial cyber attacks can be very, very severe. We know that because we see them fail for other reasons. We've seen chemical factories explode. We've seen very unfortunate things happen at power facilities. So we know what, as well as the existing cyber attacks that have occurred against industrial facilities, we know how bad those types of attacks can potentially be. Now, in terms of commodity malware getting into industrial networks, as I mentioned, the consequences of that could be very unpredictable. Nothing can happen or horrible things can happen. These systems are very, very complex. Processes are very complex. There's a lot of different control loops working together. There's a lot of different levels of systems of different types and protocols. So commodity malware could do all kinds of different things, or innocent tampering. They can do all kinds of unpredictable things. Maybe nothing, because of safety controls and the complexity of the system, or maybe something bad. Now, to do something purposeful, adversaries who want to launch an intentional attack against an industrial system need to invest a lot of time and resources, because they have to understand the process holistically. They have to understand what can go wrong and what they want to go wrong and what they don't want to go wrong. And they have to understand the mitigating controls in the environment. So even a very digital industrial control system will still have safety controls that are analog or mechanical, so pressure release valves, et cetera. And an adversary who doesn't think about those human or mechanical mitigations could try to launch a very complex attack and have absolutely no impact on the environment. And that's happened before. It's hard to launch a purposeful attack against an industrial environment. You need a lot of knowledge of the system and a lot of reconnaissance and a lot of research. So what we see is a lot of attackers as well as defenders focus on the systems at the higher levels that are more familiar. But the really advanced adversaries invest a lot of time and foothold building and reconnaissance in being able to tamper with the lower level devices. And that's what we're seeing a lot of today is advanced and well-resourced adversaries building footholds in industrial networks, not doing anything today, but learning how to attack them in the future because it's complex. So they have a foothold in the environment, in the network, and they're learning how to attack it when they wish to in the future because it costs a lot to do so. Now, the challenges we face in industrial control systems. First of all, life cycles are much longer. When you buy an industrial control system, you're usually buying it for 20, 30 years. There will be some scheduled upgrades from the vendor, but you're in it for the long haul. So these systems are used for a long time. And in these networks, the key thing is not cybersecurity. It is availability and reliability. You can't add a bunch of encryption to your protocols or a bunch of security features to your devices if they slow them down, they make them unresponsive, they add failure to your system. In the end, you're trying to do something like make water come out of pipes or make electricity safely go to people's homes. That's your number one goal. And anything that potentially causes that to fail is a big problem. So adding overhead from security controls is always a very risky choice. So it has to be done very carefully and the vendor has to give it a lot of thought. So what that means is a lot of the devices out there and protocols are insecure, but it's not necessarily terrible that the individual devices are insecure if security and mitigations and redundancy are built into the whole system and the whole process. That can mitigate some of the vulnerabilities in individual devices. And the biggest challenge is that these devices and protocols are unique, varied, and oftentimes vendor controlled and supported, so very proprietary. So we're dealing with many, many different protocols, many vendors, many devices, many firmware revisions, and they're all different and they're not always documented very well. We really need you. We need you to be part of our community. If this is something that interests you, there is so much research to be done in industrial control systems. These devices are increasingly interconnected and connected to internal networks and connected to the internet. There's a lot of convergence with IT technologies. We're starting to see things like the cloud present in industrial networks. So that's happening. So that's something that operators don't know how to secure necessarily. We're seeing substantial increases in all types of the attacks, the cyber attacks that I discussed, insider, advanced adversary, and commodity. They're all impacting these environments more and more. And our community of practice is tiny. We have a very small community of incident responders and threat analysts and intel analysts and even things like process researchers and protocol reversers. So we desperately need people, and we know that you could provide a great service to the community. We would really, really love to have you be a part of this group of people. So here's some tips if you're interested in learning more about this. First of all, industrial control system cybersecurity is a big space, just like cybersecurity in general. So when you're choosing to get into it, don't just decide, I'm going to get into industrial control system cybersecurity. Start with a vertical or an aspect. Maybe you just want to learn to do forensics on industrial devices. Or maybe you just want to learn a lot about, I don't know, like perhaps manufacturing of a specific type of device, computer manufacturing, processor manufacturing. Or, you know, I have a colleague who just really studied a lot about how eggs go from you know, chicken farms to production and into store shelves. And it's not something you think about a lot every day, but it's an incredibly complex industrial process. So pick something and read into it and learn more about it. Now, there's also consequence and mitigation modeling. We need to understand how to understand the threats that these industrial networks face. So understand both the consequences that they face on a regular basis and the mitigations, both physical, mechanical, digital, analog, that cause these consequences from happening in the environments. Remember that process engineers and operators have wonderful knowledge of their systems. So they're a great resource. If you can shadow them or learn from them, you'll never know as much as they do about their systems and their processes. And they'll never know about as much about cybersecurity as you do. So it's wonderful to collaborate with them and have meaningful discussions about the environments. And it's okay to start with the familiar levels of the Purdue model. If you want to start at the higher levels, you can do a lot there. You can contribute a lot to industrial cybersecurity just simply by starting to understand how HMIs work and industrial database servers like historians that run Windows. You can do a lot of benefit and understand a lot about how the systems work, not delving into the very low level devices that can be a little bit more different and confusing. And you're going to need to be adaptable. There's a lot of legacy systems out there. I deal with Windows 95 and Windows 98 all the time. There are a lot of technical restrictions in the environments based on, safety concerns and process concerns. And a lot of systems are supported by a vendor and they won't allow you to make modifications that they don't approve. You'll lose your support contract, your warranty, etc. So there's a lot of interesting restrictions to think about, and we have to adapt as cybersecurity professionals to those different restrictions and security concerns, and find other ways to build cybersecurity into our industrial environments. If you'd like to study ICS cybersecurity, I'd recommend you choose a specific vertical or technology to study, and choose a specific security aspect. So red teaming, blue teaming, defense, offense, forensics, malware reversing, protocol reversing, etc., pen testing even. Choose one of those aspects and study that vertical and that aspect. It's somewhere to start at least. There are a lot of pieces of information about industrial processes and devices available on open source resources, a little Google hacking, a little bit of looking on the document repository Scribd, even looking on Shodan, not poking, but looking, can give you a lot of knowledge about how industrial systems are configured today and give you access to their manuals and their security documentation. Always be willing to ask questions and be collaborative. Again, this is a small community. There are few practitioners, and industrial operators are generally very interested in talking about what they do. So people like to talk about their jobs. You have a lot of resources there. And you can always look at buying used industrial devices on something like eBay. That's an option if it's feasible and in your budget. You can oftentimes buy used PLCs for relatively cheap. There's some external training available. There's some free training available from Idaho National Laboratories on their website. There's a lot of open source protocol training available for things that are very common, like the industrial protocol Modbus, ladder logic, etc. There's some paid training available from SANS, Dragos, FireEye, and a multitude of industrial vendors. I will point you to this website. It's at my CEO's blog. He's made a wonderful list of free and cheap resources for learning industrial cybersecurity. The link is here at the bottom of the page. It's at robertemlee.org. In conclusion, industrial control systems are crucial to our society. We need them to live in the way that we expect to live. And the threats against them are increasing every single day. Industrial control systems are being connected to networks and connected to the internet at a rate we haven't seen before. And there's so much cybersecurity research and defensive tooling that needs to be done in our space. We really, really need you as part of our community. So if this is something that interests you, I highly encourage you to pursue it and explore it and find out what's available to you in this space.
So in conclusion, I hope you found this topic as fascinating as I have. And if you have any further questions, I provided my contact information on this slide. Feel free to reach out with any questions you have. And thank you again for having me. I've been so grateful to join your community here today. It's been a wonderful experience, and I'm so honored and humbled that you've invited me. Take care and have a wonderful conference.